Now let's have another applications of higher order differential equations. This time we are going to consider the spring mass system, but this time with free damp motion. So for the differential equation for free damp motion, in the study of mechanics, damping forces acting on the body are considered to be proportional to a power of the instantaneous velocity. That is, the damping motion FB is equal to directly proportional to the velocity. So FB is equal to beta times velocity. In particular, we shall assume throughout the subsequent discussion that this force is given by a constant multiple of velocity, which is dx over dt, while the constant would be beta. When no other external force are impressed on the system, it follows Newton's second law, that m d squared x over dt squared, so that is mass times acceleration, is equal to kx. This is for spring, while this one is for damping. So we're now just going to add the effect of damping to the system. So beta is the positive damping constant, and the negative sign is a consequence of the fact that the damping force acts in a direction opposite to the motion. Dividing this equation by the mass m, we find that the differential equation for the free damp motion is second derivative of x with respect to t plus beta over m velocity, which is dx over dt, plus k over mx equal to 0. So with this, we're going to replace k over m by omega squared. We're going to replace beta over m by 2 gamma. By 2 lambda. So after substituting beta over m equal to 2 lambda and omega squared to be equal to k over m, so this 2 lambda is used because this substitution will be used because it would be easier to factor out expression with the middle term, which is twice of a certain factor. So it would be easier for us to complete a square if the middle term is twice a certain constant. So we will be having m squared plus 2 lambda m plus omega squared equal to 0. So we transpose omega squared on the other side, and then by completing the square, or maybe by quadratic formula, you can get your m to be equal to negative lambda plus or minus square root of lambda squared minus omega squared. We can now distinguish 3 possible cases on the algebraic sign of lambda squared minus omega squared. So since each solution containing the damping factor e to the negative lambda t, lambda is greater than 0, the displacements of the mass becomes negligible at time t increases. So there would be 3 possible cases. So this is e to the negative lambda t, and then we're going to consider this other factor, square root of lambda squared minus omega squared. So the first case is when lambda squared minus omega squared would be greater than 0. If this happens at lambda squared minus omega squared is greater than 0, so the square root of this would be positive. We will be having real and distinct roots. If the roots are real and distinct, in this situation, the system is said to be overdamped because the damping coefficient beta is large when compared to the spring constant K. So the damping coefficient inhibits vibration or resists the vibration of the spring. So the corresponding solution would now be x of t is equal to c1 e raised to m1t plus c2 e raised to m2t. Or x of t is equal to e raised to negative lambda t times the quantity c1 e to the t square root of lambda squared minus omega squared plus C2e to the negative t square root of lambda squared minus omega squared. This equation represents a smooth and non-oscillatory motion. The figure shows two possible graphs of x of t. So an exponential that decays, or another type of exponential function, a combination of two exponential functions, the pink one. Now let us consider case 2, wherein we have lambda squared minus omega squared would be equal to 0. In this case, the roots would be real and equal. If we have equal roots, we will be having the repeated roots e to the lambda t or e to the m1t. So in the case that we will be having repeated solution e raised to mt, so another solution would be t e to the mt. So for second order differential equations. So the system is said to be critically damped because any slight decrease in the damping force would result in oscillatory motion. So this is the cutoff between overdamp and underdamp. The general solution is then C1 e raised to m1t plus C2t e raised to m1t. Or x of t is equal to e raised to negative lambda t times the quantity C1 plus C2t. So for some graphs, some graphs are given in the figure. So we have the blue one with the critical point and another exponential function. Notice that the motion is quite similar to that of an overdamped system. It is also apparent from 14 that the mass can pass through the equilibrium position at most one time. So it is possible to pass through the equilibrium position. Now for the third case, wherein lambda squared minus omega squared is less than 0. In this case, we will be having complex conjugate roots. So in this case, the system is said to be underdamped. Since the damping coefficient is small in comparison to the spring constant, the roots m1 and m2 are now complex. So we have the roots m to be equal to negative lambda plus or minus I square root of omega squared minus lambda squared. Thus, the general solution for this problem is x of t equal to e to the negative lambda t times the quantity C1 cosine t square root of omega squared minus lambda squared plus C2 sine t square root of omega squared minus lambda squared. So we change the order of omega squared and lambda squared because we want the expression to give us a real root, not a complex root. As indicated in the figure, the motion described by 15 is oscillatory. But because of the coefficient e to the negative 2 lambda t, the amplitude's variation or the amplitudes of vibration as t approaches 0 as t approach infinity. So the amplitude approach 0 as t approach infinity. So graphically, you're going to see that if it is not damped, the amplitude is constant. However, since it is damped, so the amplitude changes and it would approach 0. It is readily verified that the solution of an initial value problem, second derivative of x plus 5 derivative of x plus 4x equal to 0, with the initial conditions x of 0 is equal to 1, x prime of 0 is equal to 1 is given by x of t is equal to 5 over 3 e to the negative t minus 2 over 3 e to the negative 4t. So you may pause this recording and try to work on this. So the differential equation has the auxiliary equation m squared plus 5m plus 4 with the auxiliary roots negative 1 and negative 4, and applying the initial conditions, we will be having C1 equal to 5 over 3 and C2 negative 2 over 3. So with that, The problem can now be interpreted as having the first case with unequal roots. So the problem can be interpreted as representing the overdamp motion of mass on a spring. The mass is initially released from the position 1 unit because um, x of 0 is positive 1, so it is a positive 1 unit downward, and the velocity is 1 unit per second also acting downward. So if it is in English measurement, so we have 1 foot per second, and if it is in terms of position, 1 foot. So to graph x of t, we find the value of t for which the function has an extremum, that is the value of time for which the first derivative is 0. So if we're going to differentiate this, it would be negative 5 over 3 e to the negative t, and then negative 4 times negative 2/3, so that is positive 8 over 3 e to the negative 4 over t, e to the negative 4t rather. So x prime of t is equal to 0 for the critical point, whether it is a maximum point or a minimum point. So this implies that negative 5 over 3 e to the negative t plus 8 over 3 e to the negative 4t is equal to 0. So that would give us multiplying everything by e to the 4t. So we will be having negative 5 over 3 e to the 3t plus 8 over 3 e to the 0. So we will be having e to the 3t equal to 8 over 5. Or we can solve for t here. So that is 1/3 ln of 8 over 5. So that is 0.157. So at t is equal to 0.157 seconds, we have a critical point. So when we plug in this value 0.157 to x, to this equation and to this one, we will be having a critical point for the position. Now, the velocity would be 0 at that value. At 0.157, this value would be 0. So at x is equal to at t is equal to 0.157, we will be having x equal to 1.069, which is a maximum point. In other words, the mass attains the extreme displacement of 1.069 feet below the equilibrium position. We should also check to see whether the graph crosses the t-axis. That is, whether the mass passes through the equilibrium position. This cannot happen in this instance because the equation x of t is equal to 0 or e to the 3t equal to 2 over 5 has a physical irrelevant solution. So if we solve for t here, it would be ln of 2 over 5 all over 3. So I think it would be a negative value of time. So negative 0.305, which is practically impossible to happen because it happens at t less than 0. So the graph of x of t alongside with some other pertinent data is given in the figure. So this is the point where the position is 0. This is the starting point. We will be having the critical point here, the maximum point. And if you're going to plug in um, various points, 1, 1.5, 2, 2.5, and 3 to x of t, you're going to see decreasing value of x of t. So let's have another example. A mass weighing 8 pounds. So 8 pounds, so that is a force, 8 pounds. So if you want to compute for the mass is weight over g. So 8 over 32, so 1/4 slugs, is stretching a spring 2 feet. So 2 feet, I think there's no problem with the distance. So this is your x, 2 feet. So you can get your k from this one. So kx is equal to w. So k times 2 is equal to 8. So k is 8 over 2, so 4. So we have k equal to 4. Assuming that the damping force is numerically equal to twice the instantaneous velocity acting on the system. So BV is equal to 2V. So beta is 2 because of this. Determine the equation of motion if the mass is initially released from its equilibrium position with an upward velocity of 3 feet per second. So x prime of 0 is negative 3 because it is upward. So from Hooke's law, we see that weight is equal to 2k, or k times x. X is 2 feet. So we have k is 4 pounds per foot. So W is mg, so 8 over 32, 1/4 slugs. The differential equation is m dx over dt, or m d squared x over dt, equal to negative kx minus beta v, or beta dx over dt. So m is 1/4 equal to k, equal to negative kx, so negative 4x minus twice of, so yung beta is 2, so dx over dt. We multiply everything by 4, so we have d squared x over dt squared plus 8 dx over dt plus 16x equal to 0. So we find the roots. The roots are negative 4 and negative 4. So we have equal roots. Hence, the system is critically damped. So for critically damped system, x of t is equal to e to the negative 4t C1 plus C2t. So applying the initial condition, so there's no initial displacement applied. So at t is equal to 0, x is equal to 0. But at t is equal to 0, the velocity is 3 feet per second moving upward. So x prime of 0 is negative 3. So we find in turn that C1 is equal to 0 and C2 is equal to negative 3. Thus, the equation of motion is now x of t is equal to negative 3t e to the negative 4t. So again, this is coming from x is equal to e to the negative 4t C1 plus C2t. So when we plug in t is equal to 0, so we have C1 is equal to 0. Applying that. Now, when we plug in, or when we differentiate this, it would be x prime equal to C2t e to the negative 4t. No? So when we differentiate that, it would be t e to the negative 4t times negative 4 plus e to the negative 4t times 1. So substituting t is equal to 0. So when we differentiate this, it would be x prime equal to e to the negative 4t times C2 plus C2t times negative 4 e to the negative 4t. X prime of 0 is equal to negative 3. So negative 3 is equal to, when we substitute t is equal to 0, so C2 is equal to negative 3. So that is why we have x of t is equal to negative 3t e to the negative 4t. So to graph x of t, we proceed as in the example 3. So we differentiate this. So x prime of t is equal to negative 3 e to the negative 4t times 1 and then times negative 4. So we have negative 3 e to the negative 4t times 1 minus 4t. So we see that x prime of t is equal to 0 when t is equal to 1/4. So 1 minus 40 is equal to 0. So the solution for this one would be 1 equal to 40. So t is equal to 1/4. The corresponding extreme displacement now is x of 1/4 equal to negative 3 times 1/4 e to the negative 1. So that is by plugging 1/4 to negative 3t e to the negative 40. So that's negative 3 over 4 e to the negative 1. So that is negative 0.276 feet. So as shown in the figure, we interpret this value to mean that the mass reaches a maximum height of 0.276 foot above the equilibrium position. So the negative value indicates that the position is located upward because it is negative, so it is a position upward. Now, let us consider an underdump motion. So a mass weighing 16 pounds. So actually, this is weight. So the mass is 16 over 32. So that is 1/2. Is attached to a 5-foot long spring. So the natural length of the spring is 5. At equilibrium, the spring measures 8.2. So meaning it is stretched to 3.2 feet. So that would be your x, 3.2. If the mass is initially released from rest at a point 2 feet above the equilibrium position, find the displacements x of t if it is further known that the surrounding medium offers a resistance numerically equal to the instantaneous velocity. So we're looking for the equation of motion. The elongation is 3.2, that is 8.2 feet, minus the natural length, so minus 5, so 3.2 feet. So force is equal to the force, which is weight, is equal to kx. So we have 16 pounds equal to kx, so equal to 3.2 times k. So k is 16 over 3.2, so that's 5 pounds per foot. So the mass is 16 divided by 32. So weight over acceleration due to gravity. So we have 1/2 slugs. So we can now substitute this to the equation. Ma is equal to kx plus beta v. So what is beta? So it is further known that the surrounding medium offers resistance numerically equal to the instantaneous velocity. So force due to damping is directly proportional or numerically equal to the instantaneous velocity, which is dx over dt. So that would be this one. So kx beta v. So multiplying everything by 2. So we have acceleration and then plus 2 dx over dt plus 2 times 5. So plus 10x equal to 0. So the resulting auxiliary equation m squared plus 2m plus 10 would have roots equal to -1 plus 3i and -1 minus 3i, which then implies that the system is underdamped. So we have x of t is equal to e raised to negative t, c1 cosine 3t plus c2 sine 3t. Finally, the initial conditions x of 0 is equal to -2 and x prime of 0 is equal to 0. So let's check where does this came from. So it was released 2 feet above the equilibrium position. So that means -2. So the initial position is -2, and it was just released from that position with no other information. So meaning the velocity is 0. So x prime is equal to 0. So that is why we have this x of 0 is -2 and x prime of 0 is equal to 0. When we plug in t is equal to 0, so that would be c1 is equal to 0. C1 is equal to -2. So sine 0 is 0, cosine 0 is 1. And then when we differentiate this and substitute or plug in x prime of 0 is equal to 0, this would give us -2 over 3. So thus, the equation of motion is x of t equal to e raised to -t times -2 cosine 3t minus 2 over 3 sine 3t. Now, it is also interesting to solve for the amplitude of this equation of motion. What is the highest peak? So we can write any solution in terms of a e to the negative lambda t sine t square root of omega squared minus lambda squared plus the phase difference phi. So where A is the square root of C1 squared plus C2 squared, and the phase angle phi is determined from the equation sine phi is equal to C1 over A, and cosine phi C2 over A, and tangent phi C1 over C2. The coefficient e to the negative lambda t is sometimes called the damp amplitude of vibrations. So the amplitude is decreasing exponentially. So because it is not a periodic function, 2 pi over square root of omega squared minus lambda squared is called a quasi-period. So not a true period, but only a quasi-period. And square root of omega squared minus lambda squared over 2 pi is a quasi-frequency. So the quasi-period is the time interval between two successive maxima of x of t as given in that. So let's now consider a certain problem. Let's now consider that particular problem. So we can have your a to be equal to 2 square root of 10 over 3 and phi to be equal to 4.391. So your x of t now would now be equal to x of t equal to 2 square root of 10 over 3 e to the negative lambda t sine 3t plus 4.391.